Thank you for joining today's Belimo webinar. Today's topic will be dynamic balancing. Normally on our webinars we do more product-focused subject matters, but today we will be discussing a key point in the hydronic balancing of your building. And what we'll talk about is how pressure-dependent valves leave your building statically balanced, while a dynamic balancing comes only from using pressure-independent style valves. Let's go ahead and take a look at what we mean by static balancing versus dynamic balancing and how each of them influences your hydronic system. As we get started here, it's important to point out that the majority of the energy modeling softwares that are available commercially assume your system is dynamically balanced from a hydronic standpoint. And the reason that they make these assumptions, and assumptions is probably an unfair word, really what happens is that they ignore some of the points that become problematic in a statically balanced system. Most notably, they disregard whether or not a system has valves that are sized properly. In reality, most control valves are at least moderately to dramatically oversized. Second, we ignore the fact that there may be any instability in system pressures. The assumption is therefore made that your pressures are consistent and stable in your system at all times. And they also assume that all of your valves have what is known as a perfect valve authority, meaning that they are uninfluenced by their location within your hydronic system. As we'll see from the following examples, none of these assumptions are fair unless we're using pressure-independent valves, and therefore, if we want our buildings to behave as though in the same manner in which our modeling shows them to, we need to put the type of equipment in that matches the model. Let's first start by talking about balancing valves. We'll start with a manual balancing valve. Now, a manual balancing valve is a static device that essentially constricts the water flow area in the pipe. So if the valve is on the left and we use an analogy of an unrestricted pipe on the right side of the screen, you can see that when the balancing valve is fully open, there is essentially no obstruction of the water. Now that's not the case. There is a small obstruction and there is some pressure loss just from having a fully open balancing valve in the loop, but it's not appreciable, and so we'll estimate it as being an unobstructed pipe. When the system is balanced, the balancing valve is closed, and as the balancing valve gets further and further away from the open position, it creates a smaller area through which the same amount of water needs to pass. And this is what creates your pressure loss. In order to push water through a smaller area, we have to use energy, and in this case, the energy is water pressure. So pressure is lost as we push what should be 100% of water that in a fully open pipe through a restricted area, and this is what creates the pressure loss, which is the desired effect of a balancing valve, is to consume some of the excess pressure in the loop. The second type of device we should look at is a little bit more modern device, but still essentially a static device, which are flow limiting valves. These go by several trade names in the industry, but we're talking about a valve that is purchased with a maximum flow value. So this unit right here might be rated for, say, 10 GPM, and it will prevent your valve or your coil from ever flowing more than 10 gallons a minute. The real question with those valves is what happens below 10 gallons a minute, but we'll take a look at that as we go on. Let's take a look at what we refer to as a statically balanced hydronic system. Now we're going to use very simple examples to illustrate what we're trying to do today. My building, so to speak, is illustrated here on the right. So the pump on the bottom of the screen represents the distribution pumping from the central plant. And then I'm going to show two zones. I'm going to show one zone that is immediately adjacent to where I'm pumping, and this zone will have a fairly high pressure drop across the branch. This is because this is what's known as a direct return piping system. This means that the water flows out of the pump and directly into that first branch run. It goes through there, and then that first branch run is closest to the pump on the return, and therefore the return water is at its lowest pressure point there. So I have high pressure water coming into the first zone and low pressure water coming out of the first zone, and therefore I have a very high differential. The same argument made in reverse is why I have a low branch differential on the farthest run. The farthest loop in my building, represented at the top of my diagram, would have a fairly low pressure drop because the water has already traveled through the entire building or facility before it reaches the coil, so it's at a moderate pressure, and it is the first branch on the return run, and so the water is still moderately pressurized, and therefore we have a pretty moderate pressure drop across that coil. Across the loop. So even though these two branch runs may be identical in that they contain the same coil, same balancing valve, and same control valve, they're going to see drastically different behaviors just because of their location within the facility. Okay, so when we balance the far loop, we're going to say that that's a 4 psi coil and that the control valve was properly sized at 4 psi. And in order to balance that loop, the balancing valve will be adjusted until the flows are proper, and in this case, it needs to consume the additional 2 psi of that 10 psi branch pressure drop. So 4 plus 4 plus 2 would give us our 10 psi branch differential. If we take a look now at the closer branch run and do the same balancing exercise, we have the same equipment in place, so the coil still takes a 4-pound drop. The control valve is the same control valve that's in the other loop and was also sized for 4 psi. But since there's 20 psi of pressure in this loop, I'm going to have to constrict the balancing valve much further to create enough pressure loss to get my flow in order, and that would consume the additional 12 psi to get us to the 20 for that branch run. And so what happens now is that in that close in branch near where I'm pumping, I have a very high branch differential, and because of that I have a very high pressure drop allocated to my control valve. Let's go back to our diagram where we discussed balancing valves and see what the 12 psi pressure drop looks like. So again, our valve is wide open, our pipe is essentially unrestricted, and we have 100% of the flow of the water, and that would be the condition under which we balance the building. 100% flow has no pressure drop. And in order to get the 12 psi pressure drop, we'll turn the handle and we'll constrict the area through which the flow needs to go. And now we have 100% of the water pushing through a smaller area, and that creates the 12 psi pressure drop. This is a static condition. This is exactly what we're talking about with static balancing. At 100% of the flow, this balancing valve takes a 12-pound pressure drop. The question becomes, what if it's only 20% of the flow? What if we're at a low load, low flow modulating condition, and only 20% of the water needs to go through this restricted area? Well, I would say that that restricted area is probably plenty of area for 20% of the water, and indeed would not create a 12 psi pressure drop. Quite likely it would be significantly less, more near 1 or 2 psi, if that at all. A same argument can be made for our automatic balancing valve. Let's say that branch run required 100 gallons a minute, and so we put a 100 GPM automatic balancing or flow limiting valve in place. What happens if there's only 20% of the flow? What does this type of device do at reduced flows? Well, not very much, unfortunately. At 20 gallons a minute, very little pressure loss is created by this automatic balancing valve, and there's nothing preventing the coil from overflowing from 20 to 30, 40, 50, or even 60 gallons a minute. By the time we get to 60 or 70 gallons a minute, we'll probably start to see some pressure relief from this device, but it certainly isn't designed to hold the valve at 20 GPM. So again, when we're using systems where we're modulating consistently at moderate or low loads or moderate or low flows, both of these types of devices no longer behave in the same fashion they were when the building was balanced. One thing that's a very important point about automatic balancing valves. If you take an automatic balancing valve and you pipe it next to a standard pressure dependent control valve, it's not the same behavior as a pressure independent valve. That is a common misunderstanding in the industry. If you put a control valve, a standard pressure dependent control valve, with an automatic balancing valve, you are pressure independent when the valve is closed or fully open and nowhere in between. And so if you are in a modulating application, a control valve plus an automatic balancing valve is not equivalent to a PI valve. Let's go back to our system now and turn everything down to 20%. So my pump is at 20%, and my branch differentials are still the same because I'm controlling each one of these branch runs by a pressure differential set point. And we're going to say that we have not reset our pressure differential. just to kind of make this simple. And let's take a look at each branch run again. So at the far branch, my coil at 20% of the flow is not taking a 4 psi pressure drop anymore. However, for the sake of this example, we'll just say that it does. It makes the math a little bit simpler. So if it's still taking a 4 psi pressure drop, the balancing valve, when it was balanced, took a 2 psi pressure drop. Now it's probably taking very close to 0, but we'll call it 1 psi. And all the remaining pressure in that branch run, so we have 4 or really less than 4 from our coil, 1 psi from our balancing valve or really less than 1, and the rest of it would go to our control valve. In this case, if we assume 4 and 1, that means the control valve has a 5 psi pressure drop. Well, on a pressure-independent valve, if you overpressurize it from 4 to 5, you will see a moderate overflow. If I do the same thing at my branch run that's close in, we have significantly more pressure and we're going to see a much larger problem. So, same argument on the coil, we'll call it 4 psi. Our balancing valve was balanced to take a 12-pound pressure drop, but at this dramatically reduced flow, we agreed that it would only be in the 1 to 2 psi range. We'll call it 2 psi, and in this case, I have a tremendous amount of pressure left over for my control valve. Now my control valve is largely overpressurized and creates a very substantial overflow. This valve that's close to the building has what's known as very poor valve authority, meaning that the balancing valve is the valve that's in charge of what goes on in the loop because it has the highest design pressure drop, not the control valve. And this is the result. When the flows reduce, the balancing valve can no longer do its job of taking 12 psi pressure loss, and now I create a situation where I have large overflow in that system. In that loop. Even if I reset my pump based on the reduced flow, I may have a lower pressure drop at my far branch run. We'll call it 6 psi here, and when we balance out that loop, my control valve is only taking 2 or 3 psi. In the close run, I have less overflow here, but I still have a pretty substantial overflow because the fact of the matter is, in a direct return piping system with pressure-dependent valves, there's no way to make the first zone and the last zone behave the same way. Here's an interesting example that doesn't get talked about much in regards to statically balanced systems. Let's have manual balancing valves in all of my zones, but I have a special circumstance in my building. I have my zone closest to where I'm functioning is a very high demand currently, and the remainder of the building has no demand or is essentially unused. A good example of this might be an academic facility like a school that has a gymnasium or an auditorium or something like that close to where we are producing chilled water and distributing it. And maybe it's an evening or a weekend and we have an event like a concert or a basketball game or something. And this facility, the space nearest to where we are pumping water is highly occupied and has high load currently, and the rest of the building is unoccupied. Well, in this case, something very unusual is going to happen. Since we're sensing our pressure at the farthest loop and we need to maintain 10 psi, we have done that by reducing our pump down to whatever level drives to 10 psi at that far loop. But since the farthest loop is closed, and indeed all the loops between the far loop and the closed loop are all closed, well, that means we would only get 10 psi differential at the closest loop, because we'd have 10 psi at all of our loops. When this happens, you can see that we can actually starve this zone. Remember, at full flow, which we're going to assume we have here in our first zone, we wanted to take a 12 psi pressure drop at my balancing valve, but I don't even have 12 psi to use up here, and so we're going to run into trouble as we do this. The far zone has no pressure in it. The closed zone, we're supposed to have 4 psi on our coil, but we'll never get it because we're supposed to have 12 psi on our balancing valve, but we can't do that. And what happens is the balancing valve winds up choking this coil. And what really winds up happening is that we can't meet the demand in this space. So we have starved this coil because the balancing valve has overtaxed this line, or really it was statically balanced based on the fact that there was going to be 20 pounds in this loop, and currently there's only 10. So this can be very problematic. Balancing valves can create problems of overflowing all of our coils, but you can see another scenario here where we've caused a massive underflow that has starved this zone. Now, if we had utilized a pressure-independent valve or even a flow-limiting valve, for that matter in this case, we would not have seen this particular type of problem. Let's talk about one more thing that comes up periodically in discussions in regards to statically balanced systems before we talk about dynamically balanced systems. Statically balanced systems with reverse return piping. So all of the examples we've talked about so far have been direct return piping, which means that the zone closest to where we're pumping sees the highest pressure water because it gets the water first from the pump, and it has the lowest return water because it's the last run on the return line. Well, in reverse return piping, the inlet is still configured the same way. So high pressure water goes into my first branch run, shown here of the bottom of the two branches. But you can see here now that in addition to being the first branch run to receive the water, it's also the first branch run on the return line. So the return water goes away from the pump and then makes its way around. And so when we do reverse return piping, the goal is to pipe it in such a manner where each branch run sees approximately the same amount of pressure drop. So again, the water now is first in and first out instead of first in and last out in my first branch run. And so I can have a nice moderate 10 psi pressure drop across my first branch. And then my last branch is the opposite. It's last water in, but also last water out. And so it also has the 10 psi pressure drop. When you pipe a reverse return system, everything should be quite consistent. So if we balance this at full flow, we have 4 psi on the coil and the valve, and we have a couple pounds on our balancing valve, and then the branch close to where we're pumping is actually identical because we're dealing with 10 psi on both cases. So in light of this, when we turn the pumps down, our control valves in these cases have good valve authority because the balancing valve's taking a relatively low pressure drop. And so when we turn our pump all the way down, we might have moderate overflows on both branch runs, but nothing as dramatic as we saw with our direct return piping system. So in light of the fact that reverse return systems appear to quell some of the problems we have with static balancing, why aren't they more popular? Well, the answer really comes from cost and installation. The cost of a reverse return piping system could be anywhere from 50 to 60, even 70% more expensive than piping a traditional direct return system. All this additional pipe obviously has to add additional funds. The other problem with it is that it's easier to draw up on paper than it is to install in a building. To get all of these pressures to be identical, all the piping runs have to be close to the same length, if not exactly the same length. And so if you wind up with a lot of longer runs versus shorter runs, it's not nearly as consistent as it would be as we show here on paper. That said, it's still going to be a whole heck of a lot better than a direct return system. But again, the number one point driving people away from this is cost, and secondarily is the complexity of the install. Again, if we reset this thing, we'd see pretty much the same thing. We're going to reduce the overall pressure because the flows are lower, and then we have a real nice clean system if we use VFD reset in addition to a reverse return system. Okay, so we've showed you several ways to statically balance the system, and we've pointed out a lot of pitfalls that come along the way. Let's take a look at what happens when you dynamically balance the system. Well, a dynamically balanced system is a whole lot simpler to explain. We're going to put pressure-independent valves at all of our loops, and therefore we're no longer concerned about things like valve authority or how much pressure is in that loop, because the pressure-independent valve is designed to provide a specific amount of flow regardless of the pressure in that loop. So my coil and valve that are in my far loop, which are identical to the coil and valve in my close loop, can now have the same behavior because of this pressure independence of the valve. So whether I'm at full load or part load, or some zones are open and some loads are closed, I'm going to get the exact GPM needed at the far coil, and I'm going to get the exact GPM that's needed at the near coil. This is why we call it a dynamically balanced system. Pressure-independent valves are not balanced at a static point, and they don't have a set point for a specific GPM. They're designed to modulate through the whole range and remain pressure independent at all of those spots. This allows us to take very dynamic, if not chaotic, systems and make them as balanced as possible by using this type of technology. There are several benefits to using dynamically balanced systems. The number one benefit, obviously, is that all zones are balanced at all loads. We have perfect valve authority, and this will eliminate the hunting for your set point, and it should reduce the occupant complaints for discomfort. In addition to that, we're going to prevent overflows. And anytime we can prevent overflows, we can improve the delta T at our coil and potentially lower our costs for pumping water. And we never need to rebalance these devices. Since they're dynamically balanced, if you change your equipment or possibly add something to your system that would normally constitute a rebalancing of the hydronic side of your system, that would never need to be done with a pressure independent valve. So whether you've added zones or changed your equipment, you're still good to go. Thank you for joining our webinar today. If you have any further questions, please feel free to reach out to your local Belimo area representative or check us out on the web at www.belimo.us. Belimo offers a full range of pressure independent valves, both mechanically and electronically pressure independent, and any one of our Belimo representatives would be happy to give you more information about these products.